Yeah.
Oh, yeah. I feel like he and Alessandro together.
This model is kind of like don't go past 3 weeks.
Should I begin? Okay. All right, so. No, I'm fine, thanks. Okay, so now I'm going to, today we're going to start by doing some explicit calculations. So first, the weak interactions. Which have been mentioned several times. So let's look at B to C, mu E to E. This comes into semi-leptonic B decay, or the corresponding mu decay, where you would have a muon and a muon neutrino up top. And the amplitude here is there's a minus IG over root 2 squared. The root 2 is just historical, Y the weak coupling, the W coupling for the square root of 2 there. And then you get a VCB. And I'm going to write fields down, but represent the spinors, U of the momentum, et cetera. And then you get the W propagator, which is minus I over k squared minus mw squared. And at this level of constructing EFTs, we're saying that k is much, much less than mw. And so it's trivial in this case. It's just, as I said, at a tree level, things are basically just a Taylor series expansion. So you take this object, and you write it as minus I over minus mw squared. And then you get 1 plus k squared over mw squared. Just some expansion like that. And so if you go back up to the Lagrangian level, then some operator in the Lagrangian basically has a Feynman rule, which is I times whatever the fields you have. So you drop one factor of I from here, and you get an effective Lagrangian, which is, again, for historical reasons, is written as minus 4g Fermi over root 2 VCB. And then I'm just going to put the fields back. Okay, here. And this expansion, you can think of the one term as this operator. So I'm going to simplify things. And then there's a k squared over mw squared, et cetera. So you should really think of these as independent operators. The one term is just the 4 fermion operator. The k squared term is an abbreviation for one derivative on the left-hand operator and one derivative on the right-hand operator. The next term will have 2 derivatives and 2 derivatives, et cetera. And at this level, the coefficients are kind of trivial. It's 1 over mw squared, 1 over mw fourth, et cetera. But when you start doing radiative corrections, they're not going to be simply related. And the anomalous dimensions will be different, et cetera. And from this calculation, you can see that 4g Fermi over the square root of 2 is just g squared over 2mw squared. There's a root 2 here, so that's a 2, and then the mw squared there. And what is it? mw in the standard model is g times the vev over 2. So this is 2 over the vev squared. Okay, so again, the normalizations and stuff is just for historical reasons. So if you measure mu decay or semi-leptonic B decay or whatever, you find out what the scale of the weak interactions is, which is the vev from here. And from in the old days, you cannot get a prediction for what mw and mz are from this. And so people didn't know until parity violating experiments measured sine squared theta how to get what the W and Z masses were. Now you can see from here, OK, so this operator is dimension 6. It's a 4 fermion operator. It's dimension 6. Its coefficient is 1 over v squared. The next operator is dimension 8 because it has 2 more derivatives. Its coefficient is 1 over v squared times 1 over mw squared. So you might naively think, by looking at the first term, that, oh, I can use my effective Lagrangian all the way up to 250 GeV. But that's not true because the next term has a 1 over mw squared. And so there are some scales which are related, but you can't, just knowing one term doesn't necessarily tell you where the new physics comes in because you have a coupling constant, little g in there. And by comparing dimension 8 to dimension 6, you would conclude that, OK, the theory breaks down at closer to 100 GeV, not 250 GeV. OK.
In that point, please, how do you know that the theory breaks down at 100 GeV?
Just because if you looked at the dimension 8 term, it would be 1 over v squared, 1 over mw squared. So by doing more precise measurements, you would notice that there was this term. Historically, what people did was they looked at gamma z interference and e plus e minus to mu plus mu minus, and you see the cross section start to rise. And that's, again, looking at, basically, you're starting to see the k squared minus m squared structure of the propagator. And that's telling you there's a pole. I mean, something's happening at a much lower scale than you might have thought. OK, so if I start with this effective Lagrangian, let me not write it again. I can then go calculate B decay, which is going to be through a 4 fermion operator. And in this particular case, if you do the calculation, VCB squared, G Fermi squared. So if you haven't done this, you should do it. There's the corresponding thing for the muon. And then there's some function of rho, where rho is mc squared over mb squared. And this function is 1 minus 8 rho plus 8 rho cubed minus rho fourth. OK. So what I want to emphasize here is when you start doing this calculation, this rho is depending on 2 low energy scales, if you want, m charm and mb, which are scales in the effective theory. And the entire dependence on mc over mb is retained in the effective theory calculation. This is just coming from the 3-body phase space integral in the EFT. So what you're expanding is you're dropping terms which are mc over mw and mb over mw. But any 2 low scales, in this case mc over mb, or if you put in the electron mass or whatever, the entire dependence on this is retained in the EFT calculation. You had a question? Yeah.
Yeah, thanks. Is there some way to see where those coefficients come from in that function, in that f?
No, you got to do it. Gotcha. Yeah. So yeah, here, I mean, so it's 3-body phase space, and you just have to do the integral. OK. Now, so at this level, it looks trivial. But when you start doing higher order corrections, so you have a W here, and now you stick a gluon there. In the EFT, the corresponding calculation is going to be a radiative correction. I guess I should draw my gluons the same way, to a 4 fermion operator. And once you start putting in alpha S corrections, the EFT method is far, far easier to do. And I think it's fair to say that basically in these calculations, nobody has ever done the analog of the resummation of the leading log resummation and so on using the full theory. It's just never been done. It's too hard. And so I'll sketch what you do. OK, so now we come to the non-trivial part, which is loops. Because without that, I think EFTs are basically just series expand. So take this G Fermi operator, the 4-quark operator, 4 fermion operator. And imagine, OK, so it's dimension 6. And imagine calculating a diagram like this. Okay, this is the penguin diagram. And OK, so you have to decide why it looks like a penguin. But what is the integral you're going to get? You're going to get some integral d to the dk let me not put in all 2 pi's. And you're going to get some k squared minus m squared, because, just schematically, because there are 2 fermion propagators each giving you a 1 over k slash. So there's some k squared minus m squared structure. So it's in 4 dimensions, this is quadratically divergent. And you will often see people wave their hands and say that this goes like some cutoff square. And if you had a dimension 8 operator, so this is dimension 6. If you had dimension 8, so this, wherever it's gone, there are 2 more derivatives in there, which means at this vertex you will get 1 factor of k from each derivative. So you're going to get k squared over k squared minus m squared, which will go like cut off to the 4th, and so on. And my EFT amplitude was, there was some 1 over m squared from here. And then the loop gave me cutoff squared. And then the dimension 8 was an 1 over m to the 4th. The m here just stands for either mw or v or whatever. It doesn't really matter. And then you get a cutoff to the 4th. And now if you say, well, my EFT is valid up to this high scale, then all of these terms are order 1. You have no expansion. And the entire thing breaks down. So you have a meaningless calculation because, at the loop level, the whole thing fails. Now, let's go back and see what we're trying to do. We have this EFT. There are all these low scales. We're trying to get the entire dependence on the infrared scales. Yeah?
Over here, could you not put your cutoff below your heavy mass scale?
You can try and do that, but then you will have trouble with the matching and so on. And I'll come back to how you actually do it, which is much easier than that. But if you look at the analytic structure of scattering amplitudes and so on, you get cuts and various things, and they're all governed by the low energy scales. And your EFT has to reproduce all of that. So it has to reproduce that function f of rho in this example. And what's happening is that when you start doing these kind of calculations, so I just put the energy here, and there's some IR here and UV. My tree level theory and everything else is getting stuff correct in the IR by construction. And now when I do loops, I'm integrating up to some, effectively to infinite energy. And the integrals are just wrong in the UV, because the momentum dependence of the theory is not the same as the full theory. We haven't kept all of those propagators, et cetera. And the point is that if you take the EFT result, and in some sense the full result, the difference is purely UV, which means it is local as long as you're looking at low energies. So the difference is some bunch of local operators. And what we do in what is called matching is figure out what the local operators are. So what happens is that if I do this at one loop, this coefficient of this 4 fermion operator was 1 or in some units. And when I do the alpha s expansion, there will be some correction here, which is order alpha s times some number. And this number has to be chosen so that the full one loop result is correctly reproduced by the EFT. So I'll show you how to do that in just a second. And so what you need for the EFT is essentially some method where the loops respect the power counting, because we saw that the whole point of the EFT was we had this expansion in low scales, p's, I call them p's over m. And that's our expansion. It's part of the definition of the EFT. It's telling you what is dimension 6, what is dimension 7, 8, et cetera. And if the loops mess it all up, then your starting point was not sensible. So you want to make sure that the loops respect what's called manifest power counting. You should be able to read off the powers. Yeah?
Where is the
So the Lagrangian is minus 4 GF over root 2 VCB which way was it? And then there's a C1 here. And at tree level, okay, our calculation shows that C1 at tree level. That's what I mean. And there will be a one order alpha correction, which we can calculate. So I won't do this precise one, but a very similar calculation where you can do it in much less time. Yeah?
So that number is actually coming from the dimension 6 operator at the next loop.
The one is from this tree level. Yeah, the alpha S.
Yeah.
Yeah, it's going to come from figuring out the difference between these two diagrams. So we'll do a toy example of the matching.
So do you match between dimension 6 operators? Or do you also have to match the next operator?
We'll do the whole thing in like 2 minutes. I mean, as I said, for a toy example rather than this, because I don't want to keep the whole gamma matrix structure and everything. OK. So the answer to all problems is dimensional regularization. And let me just write the answer down. So this is, OK, you can go look this up. And OK, the formula is not too important, but anyway, let me put it down. What is it? Gamma A plus D over 2, gamma B. But the important point is that you get m squared to the d over 2 minus a plus b. One second. The integral only cares about what the mass is in the denominator. There's no cutoff. There's no nothing. Even if this integral is quadratically divergent, you only get the m over here. If you have multiple denominators, k squared minus m1 squared, k squared minus m2 squared, then you can use Feynman parameters to combine this into some kind of integral dx, k squared minus m1 squared x minus m2 squared 1 minus x whole squared. But again, you can see that the scale here is just some linear combination of the two m's. So if you have propagators where every denominator is a low scale, doesn't matter how many you have, this m is going to be a low scale. So in some sense, you should think about dimensional regularization like integration by residues. There are poles in the denominator. And what you're getting is, in some sense, the contributions. This is schematic, but it's the poles are determining the momentum. And you're getting contributions from these low scales. You had a question? Or?
Yeah. Since we are going to move away from that for the toy example, I wanted to ask if you were going to talk at all about gamma 5 and dim reg.
No. We have enough problems as it is. Yeah. OK. So really the only thing you need, OK, I'm sorry. In dim reg, you have to put these mu to the 2 epsilons over here in the couplings. And so the analog of the cutoff in dim reg is the mu, but the mu only comes in with fractional powers of epsilon. And so what you can get is a 1 over epsilon times a mu to the 2 epsilon, for example, which when you start expanding in epsilon about 0, because you're in 4 minus 2 epsilon dimensions, will give me a log mu. So in dim reg, this mu scale, the analog of the cutoff, but in dim reg, a mu only occurs in logs. Okay? There are no explicit powers of mu anywhere. So this immediately gives you what I wanted, which is manifest power counting. So if I have some diagram with some m's here, 1 over m squared and a 1 over m squared, and I do the integral, doesn't matter how divergent it is, you can never get any powers of m from the integral, because none of the poles, nothing in here has a high scale in it, because this is an EFT diagram, and all these particles in here are all light particles. Everything which is propagating is light, because those are the only fields in your Lagrangian. So the only thing you can get in the numerator are little m's. You can never get a big M. And so the big M counting is exactly the same as what we had for tree level. There's no change at loops. Here, this is like the basic point. You can just, it's manifest 1 over m counting. So if I take this loop diagram and it effectively produces an operator which is O to the d over m to the capital D, I'll just call it little d was 4 here, then we know at tree level that d minus 4 was the sum of di minus 4 over all the vertices that I have. So this is the power counting formula. Just 1 second. And this is true even including loops. So there's no change. Yeah? I can't hear you. Because now you can have powers of lambda upstairs. So here, you might get little m squared over m to the 4th. With a cutoff, you could get lambda squared over capital M to the 4th. And now you have to decide what lambda is. OK? And I mean, maybe a more fundamental reason, lambda has nothing whatsoever to do with the theories, just something you put in by hand. And if you were doing calculations using scattering amplitudes, for example, where you would try and reproduce this loop diagram by cuts in here, then there's no lambda anywhere in the calculation. And you're using analyticity and so on to construct the logs and so on for loops. And to introduce terms like this, lambda would be a parameter you just made up. It had nothing to do with the theory. So anyway, so it's bad. The other thing is cutoffs are horrible anyway. They break gauge invariance, they break chiral invariance, they break all sorts of things. And historically, I mean, even in chiral perturbation theory, people were getting pion mass contributions from the loop level proportional to cutoff squared. And you know you can't have that. Pions are Goldstone bosons. The mass has to go to 0 if the chiral symmetry is exact. And then Weinberg and Jakiv and people figured out how to add counter terms and things to make sure the chiral invariance is restored, because you broke the symmetry by the cutoff. And then, I mean, now we just use dimensional regularization, because it respects both gauge invariance and chiral invariance. Yeah.
I guess I was wondering, between these two examples, cutoff, obviously, you've shown us that it's kind of bad for not just the several reasons you mentioned, but also it breaks down this manifest power counting. Is there, I mean, other than just picking bad regulators, is there any other type of problem that can ruin your manifest power counting, even if you use different regulators?
Not that I know of here, no. I mean, OK, let's put it this way. All calculations done, any calculation which calculates some experimentally measured quantity, an observable, beyond tree level is all done in DIMREG now.
So there aren't like other things.
There's no option right now. We don't have an option.
I mean, there aren't other things to really watch out for. It's just pick DIMREG and you're safe. Is that something?
No, I wouldn't make that statement. I mean, there are some subtleties connected with anomalies. That's one subtlety. We haven't found others. But as I said, there are no proofs. Yeah. Yeah.
And in DIMREG, are you integrating up to infinity or integrating up to mu?
No, you're integrating to infinity.
OK.
OK. Yeah, maybe that's a good point. This integral is over all k. And the point is, I don't care what's happening up here. It's wrong. But I'm going to fix that by the matching. And the point is that everything in the infrared is correct. The UV is maybe wrong, but it's local. So what I'm going to do is fix that by adding in some correction here to reproduce the fact that the UV of this operator is not the same as the UV of this whole thing. So I'm just going to do an explicit example where you can do it. Okay.
Even if we have some such a cutoff biodiversity or something like that, in the end we add a counterterms to cancel these terms. Say what's the difference?
Yeah, because you've introduced a new scale in your theory. Lambda is some dimensionful parameter, and now you've broken down your entire expansion because you're expanding in. So what are we doing in the weak interactions? We have a physical scale, which is MB, and we have W, which is another physical scale. It's the W mass. And everything is dependent on those masses. And now you've just put in some random lambda. And what is it? OK, it's something you made up. And now if you take lambda to be big, this expansion breaks down. If you take lambda to be small, how are you going to do the matching? Because you don't know what's happening in the UV, because your integrals don't have the UV in them. OK. So anyway, don't ever use a cutoff. It's just going to make your life hard. OK. Now, there's some interesting features of dimensional regularization which are worth noting, which is that the only problem. OK, so I said that there are infinities, these 1 over epsilons, which are we have to subtract with counterterms, which I'll come back to. But there are no power divergences. And what I mean by that is that if I have an integral like d4k over k squared, which is quadratically divergent, in dim-reg, that's just 0. OK, there's nothing there. The only divergences you get are log divergences. And that you just plug into this equation and see what happens. The other thing I'll mention is that, OK, here's this famous diagram that people draw for the Higgs, which is d4k over k squared minus m squared. And if you, OK, so I think I would recommend everybody do this diagram. This is like the simplest one-loop diagram you can possibly do. And you get 1 over 16. OK. I should have written the exact answer down, but it's 1 over, I think it's log mu bar squared over m squared plus 1. OK? So it has dimensions of mass squared. Again, in dim-reg, the only masses which can occur are the physical masses in the poles in the denominator. That's m. You get this. There is no cutoff squared contribution to the Higgs mass. Just go take this diagram. It's in Peskin and Schroeder, probably. Do it. And see what you get. OK? So a lot of these arguments which are hand-waving are fake, because you have to actually do a calculation and see what you get. I should mention, OK, so presumably you've seen this in dimensional regularization, but at the vertices, you get factors of mu to the 2 epsilon, and then because of these 4 pi to the d over 2s, this mu bar squared is by definition, what is it? It's, I don't remember what it is anymore. It's 4 pi mu squared e to the minus Euler gamma or something. That just to get rid of some factors of 4 pi, fractional powers of 4 pi, and things in the expansion of the gamma function. So this is just called ms bar versus ms. It's kind of irrelevant. OK. Yeah.
Sorry, did you finish the point you were trying to make about
Yeah. So what I'm saying here is that if I take diagrams like here with 2 factors of m squareds or whatever, there are never any m squareds in the numerator. Well, basically, the only m squareds you get are explicitly vertex factors now, like the G Fermi. It's the Feynman rule for this dot. The integral doesn't depend on big M, and you never get any big M's from that. So you can get the total power. So this diagram is 1 over big M to the 4th, because it has 2 m squared. So that's what I mean by manifest power counting. You can just read it off from the diagram. And so that's all this formula says. An operator of dimension d has d minus 4 in the denominator. So if I have vertices like this, every vertex has a power in the denominator, which is the dimension of the operator minus 4. And you just add them up. And that's the result you get for the final operator. And the offset of 4 is just because of the Lagrangian being, yeah. OK. Now, when you do these diagrams, you can get 1 over epsilon divergences. I mean, 1 over epsilon in one loop, 1 over epsilon squared at 2 loops, and so on. And so you have to renormalize. And you have to add counter terms, which cancel the 1 over epsilons. And that leads to renormalization group evolution and running of coupling constants and so on proportional to these counter terms. Now let's go to our usual Lagrangian, which was d less than or equal to 4 plus L5 over m, and so on. So a renormalizer, what people call a renormalizable theory, is only got these L's with dimension less than or equal to 4. And we saw that really, even though the L d less than or equal to 4, the power counting tells you that all of these operators, in the sense of I'm counting powers of some low scale over capital M, all of these are effectively all d equals 4 operators, because a mass squared operator had 2 powers of a suppression, a fermion mass had 1 power. We discussed this last lecture. So now the di minus 4 is equal to 0 for everything in here. So if I do arbitrary diagrams, this formula tells me that I'm going to get 0 for the d minus 4 of the net result. That means that if I start with this Lagrangian, all my counter terms are still in here. And that's the standard renormalizable theory. You renormalize the mass and the coupling constant and so on, wave function in QED. But in an EFT, you have at least one operator which is higher dimension. So take any operator. If you have some higher dimension operator, d minus 4 is some number which is bigger than 0. As soon as you have one number that's bigger than 0 and you start putting multiple loops in here, you can generate arbitrary high powers. OK, that's the difference between the two. What that means is the series can never stop unless your theory happens to be a finite theory. But interesting theories are not finite. Sorry. Interesting theories with experimental applications are not finite. So you're going to get the whole series. OK, so it's important to note you cannot truncate this expansion. Even if you thought your coefficient was 0, there's an infinite counter term you need to regulate this. And now you can see how anomalous dimensions are also going to work. Because if I have some, I'll call it C5, some dimension 5 coefficient. Yeah, go ahead.
Thanks. So you said even if your coefficient is 0, you still need a counter term for it?
Yeah, because there may be some C6 operator which is 0, but then a loop of 2 dimension 5s gives you some 1 over epsilon which is infinite.
OK, and that same so why?
Well, it'll be 0 at tree level, but radiative corrections won't preserve the 0.
OK, thank you.
Yeah. So at some order, you might get 0, and then, But suppose I have a running of a dimension 5 operator. Well, again, you just got to get used to counting the m's in the denominator. So if I do mu dd mu of a dimension 5 operator, it's going to have something times dimension 5. I mean, there may be multiple operators. So there could be some index I, j, and there could be some gamma ij. And this can depend on g squareds and dimensionless parameters. If I have the running of a dimension 6 operator, well, now I need 2 powers of m in the denominator. I can get something times dimension 6. But I can also get something else times 2 factors of dimension 5. OK, because each one has a 1 over m in it. And so two dimension 5 insertions can give you dimension 6. And so on. If you have dimension 7, you can have 7, 6 times 5, et cetera. So you can read off the structure of the RGE by, just this has a 1 over m squared. This is 1 over m squared, and this is 1 over m quantity squared. That's so the m's have to match the powers of m. Okay, so that's how the RGE will work. Yeah.
Does the mass scale for different operators has to be the same?
Okay, so already last time we discussed, for example, baryon number violation, which came with some 1 over m gut squared, and that was dimension 6. And here the Fermi theory has a dimension 6 operator, which has 1 over mw squared. And so if you started with the Fermi theory, you might conclude that, OK, the baryon number violating operator is also suppressed by 1 over mw squared, and then your theory would be dead. But there's a symmetry here, which is baryon number. And so you can have sectors where there's one scale, let's say, for delta B equals delta L equals 0 operators. And then there can be a different scale for a delta B not 0 operator. And you could have a third scale, and happens in leptogenesis models, for delta L not equal to 0 operators. Okay? So you can have multiple scales. I mean, the things rapidly can get complicated.
Yeah, so if we get multiple scales, then because it's hard to just do a simple bulk count.
No, you can still do, you can count the individual scales. So if you have a baryon number operator, which is dimension 6, you can't get G Fermi in there because this operator doesn't violate baryon number. The diagram is going to have some insertion of baryon number, but then the baryon number insertion is going to have the m gut in there, et cetera. So you can keep track of this from powers of the symmetry breaking and so on. Yeah. OK, other questions? Yeah.
What about mixing those scales? If you power count, can you always factorize it?
Yeah, we're treating these scales as widely separated. If they're close together, like MW and MZ and so on, there's no separation. Yeah. OK, so let me start again. So now I want to do a toy example. And how much? And it's similar to the weak interactions, but I just don't want to deal with all the gamma matrices and propagators and everything else. OK, so I'm just going to start with some kind of, as I said, it's a toy example. So suppose I have some interaction, which I'm just call some GL. The sum operator x, for example, let's make this f mu nu squared or something. And then there are two phi's which are light. So this is already dimension 6. So the GL has some 1 over m squared in it. It doesn't really matter. OK, so I'm going to consider just the dynamics of one light scalar and one heavy scalar. So the light scalar has some mass little m. The heavy scalar has mass capital M. Now I would like to get rid of the heavy scalar and look at the EFT where only the light scalar is propagating. And whatever the x is, whatever. So in the end, what I'm really doing is doing an EFT for an integral if you want. But we can do it this way. OK, so the EFT can only have, well, it has the x and phi, but no capital phi.
Sorry, the f mu x goes like f mu nu squared?
Anything, some fields in the light theory. It doesn't matter what it is.
But these are all dimension 4 right now?
No, this would have some. It doesn't even matter what it is, as you'll see. Yeah. OK. So if I work to lowest order in G, so I work to order G at tree level, well, what do? You just erase all the heavy fields. And this operator, so you have some amplitude, like phi goes to x. So if x was f mu nu squared, it would be phi to gamma gamma. In the full theory, it's given by some diagram from this object. In the EFT, it's the same. So LEFT at this order is just 1/2 GL x phi squared. Now, if I go to order G squared, again at tree level, I can have a diagram in the full theory with only, okay, so what I'm matching is S matrix elements or scattering where there are only light particles in the external states, because that's all that the EFT has to describe. So I can have a diagram which looks like this. There's some x here, phi, capital Phi, x, and little phi. This is similar to the Fermi theory. There was a W going across. Here there's a capital Phi going across. And what do I get from here? This diagram has two of these vertices. It has an I over some k squared minus big M squared. So I'm sort of mixing amplitudes and operators at the same time. And then there's some operator x phi here. Let's put it on the left. And there's another x phi. And this k is like the k being transferred from one operator to another. So if you have Fourier transformed it, this x phi would be at k, and that x phi would be at minus k, so that momentum is conserved. And this k is the transferred momentum. And so like in the weak interactions, I can expand this whole thing out. And in the interest of time, let me not worry about signs and stuff. You can look at the notes 1 second. And so I get x phi 1 over m squared, exactly as in the other case. Yeah.
In the EFT, is the big phi that's internal there?
It's not there.
As like an off-shell particle?
No, no, no. This is not in the EFT. This is in the full theory.
Okay.
So now, this diagram, this operator, which is all I have in the EFT is this. It's producing some scattering, but it's not getting this amplitude right. It's missing this diagram. Okay, we're doing this in perturbation theory. And so now I need something in the EFT to reproduce this amplitude. And what is that? It's basically this, exactly like in the weak interaction. So I can schematically say there's some g squared, there's some x phi, 1 over m squared plus and let me think of this x phi. This is some C101 operator 1 plus C202, etc., where O1 is just 2 x phi's. O2 is d mu x phi times d mu x phi to reproduce the k squared. O3 will have 2 derivatives, etc. And C1 is just 1 over m squared. C2 here is m fourth, 1 over m fourth, and so on. Okay, so in some sense, if I can't Taylor expand. Okay. If I just pull out the powers of m, then at this tree level, all the c's are 1, just like in the weak interactions. Okay, but the non-trivial thing happens at one loop. So let's look at what happens at loop level. So you can have loops where there are 2 x's, and there are 2 light phi's in the full theory. We don't need to worry about it because we already have this vertex in the EFT. So exactly the same diagram is there in the EFT as well. So this works. There's a diagram here where there's a heavy phi going around. There's no analog in the EFT. And so you would calculate this diagram, and this would give you something similar to this tree level calculation, which would be some matching. But but what I'm interested in is not this, but the third class of diagrams where there's one light phi and one heavy phi going along. Yeah.
So can you repeat why you mentioned the second one?
It's okay, we can do it. It's just giving you d4k. Actually, we can do it. So it's giving you this times 2 x's. And so that's, OK, thanks for asking, so because this is useful. You're going to get log mu bar squared over m squared. That's what you get. Squared. OK. So this is missing in the EFT. So I would add, you drop the I because the Lagrangian term gives you, the Feynman rule has one extra I in it. So this will give you an operator in the Lagrangian, which is some 2 x's, so f mu nu to the 4th, let's say, over 16 pi squared. There's a, whatever this g was, g heavy squared. So the dimensions are in g heavy to make it all work out. And then you get a log mu bar squared over m squared. And that's the answer. And you can see that if I match at a scale mu bar, which is of order the heavy scale, it doesn't have to be exactly that. This is not a large log. Large logs are important because they lead to a breakdown of perturbation theory. And we'll figure out how to sum them. So this is just a straight matching. That was tree level. But I wanted to focus on this diagram. So in the full theory, I'll call this IF. This is an integral, which is, OK, let's just call it 4, but we're going to use dimensional regularization. It has one light propagator and one heavy propagator. And the reason I'm doing this toy integral is because these are simple integrals to do. So you can do this. Oh, and there's a g squared here. So this is I g squared over 16 pi squared. 1 over epsilon minus log m squared over mu bar squared plus little m squared over big M squared. OK, so this is, you combine the two denominators using Feynman parameters, use the formula to do the integral, do the x integral, and this is what you get. OK, so as I said, all the logs, mu bars only occur as logs. You have non-analytic structure in the infrared scale. You have little logs of m squared, which are, you can think of them as non-analytic in IR. If you had put in external momenta or something, you could have gotten logs of p squared. And you have things which are non-analytic in the UV scale. You have logs of big M squared. Yeah?
Sorry, in the integral, we run d4k, but are we doing?
We're really just doing dim reg. Let's just, and there's a 2 pi to the d, et cetera. Yeah. So that's what I get. And this is, so you can see there's a divergence, there's a counter term, et cetera. So you need to renormalize. So everything we need is in this toy example. Yeah?
So I have a question about the leading order calculation.
Yeah.
So it looks like now you just solved the equation motion for capital phi and plug it back. So can I say that by matching the leading order diagram, what I get is equivalent to what I get by solving the equation?
Yeah, at tree level, it's equivalent, I think. Yeah. OK, but now I want to compare this with the EFT calculation. So what's interesting here is that we have a contribution to exactly this process from the EFT. So because at tree level, I got this whole infinite series of operators here, which I could treat as an x and a phi and another x and a phi, where that intermediate capital phi propagator has been shrunk to a point, just like in the Fermi theory, where you went from 2 currents to a 4 fermion operator. So there's a hidden phi propagator in there, but it's been expanded out. Now, this is sufficiently simple that you can see what happens when I do the EFT diagram. So these are all EFT operators. OK, it's right here. These are vertices in the EFT. So I have to do the diagrams from that, which look like this. There's a phi loop. And what are they? Well, we know what that thing is. So if there's a momentum k running around here, this is simply g squared d to the dk over 2 pi to the d. This phi propagator is in the EFT. It's 1 over k squared minus m squared. But what is this vertex? This vertex is simply the expansion of this k squared minus m squared, because that's where it came from. It came from expanding this 1 over k squared minus m squared. So the EFT has a sequence of diagrams, minus 1 over m squared, minus k squared over m fourth, et cetera. This is the contribution from what I call O1. This is the contribution from O2, et cetera. Because every term in the Taylor series expansion here, the 1 over m squared is O1, that's O2, that's O3, and so on. So the difference in the two is whether you expand before the integration or not. So this is the EFT integral. Yeah.
How do you know when you can terminate your expansion?
Well, we are working to some order in capital M. So typically, you would be working up to dimension 6 or something, and you would just keep the first term. Here, so the reason for the toy example is it's sufficiently simple that we can do all of these pieces at once. And in the weak interactions, you cannot. In most theories, it's just too hard. So you would just work to, you would typically work to dimension 6 or maybe dimension 8. I mean, that delta S equals 2 processes and things which are second order weak, and you just stop there. So in principle, just think of this as order by order. You do the lowest order, and then you go back and start again and go to one high order and keep going. But here, this is sufficiently simple that we can just do it. OK, and what do you get? OK, so these are sufficiently simple integrals that you should just use the Dimrag formula and do them. OK, and what do you get here is IG squared over 16 pi squared times the 1 over m squared integral gives me minus m squared over m epsilon plus m squared log m squared over mu bar squared minus m squared. And then the 1 over m fourth integral gives me basically the same structure times an extra m squared, et cetera. OK, as I said, these integrals are sufficiently simple that you can just do them all, just using the same standard Dimrag formula. And the main, OK, so I'm going to call this IEFT. And the main point is that IEFT is simply not equal to the full theory result. OK? And so doing the expansion changes the result. You can think about it, again, if you think of it by the method of residues as schematically, this gets contributions from the pole at little m squared and from the pole at capital M squared. Here, when you expand it out, there is no pole at capital M squared, even though because you're doing integrating term by term. And you're getting this contribution from little m squared, but you're losing, in some sense, the contribution from capital M squared. OK, so if you don't believe me, I mean, these are, as I said, these are very simple integrals. At least the EFT one, there's only one propagator. And just k squared over k squared minus little m squared, you can just do them and see. OK, so several points to make here. Well, first, of course, these are not equal. So the other point is the 1 over epsilon terms are different. So here, the 1 over epsilon coefficient just had a coefficient 1. 1 over epsilon term had a coefficient 1. Here, you have the series of little m squareds over big M squareds. You can sum them up, but it doesn't add up to 1. It adds up to something else. So the EFT and the full theory have different, so the anomalous dimensions change from the full to the EFT. They have different anomalous dimensions. Yeah.
What is an anomalous dimension?
So if you haven't seen anomalous dimensions, then just say that the counter terms you need are different in the full and the effective theory. The divergent part is different in the full and effective theory. The anomalous dimension is related to the, yeah, I'm not going to be able to have time to describe how to do the anomalous dimension, but it's basically the coefficient of 1 over epsilon. At one loop, it's just minus 2 times the coefficient of this 1 over epsilon. So the statement that the counter terms are different. So you have to renormalize the EFT using a different set of counter terms in the full theory. The EFT is a field theory all by itself. It's sort of independent of the full theory. It has its own counter terms and own renormalization procedure. Furthermore, so this difference between the two is what I would call the matching. So what is called the matching contribution, which is the extra piece I have to add to the EFT Lagrangian because I'm not getting the amplitude correct. I have to add a matching contribution, is given by taking the full theory plus the full theory counter terms, which in dim reg just means drop the 1 over epsilon piece, just keep the finite part. And I subtract the EFT plus its counter terms, which are different counter terms, which just means just drop the 1 over epsilon and just keep everything else. And that tells you the mismatch in the two theories. So this is an example of a one-loop matching, the analog of the alpha S correction and the weak interactions that I was talking about. There it's a little more complicated because you have to put in the whole, the gamma matrices and everything in the box diagram. But in some sense, it's really not very different from this, just more algebra.
I have a question.
Yeah.
So in order to get the correct result in the EFT, you have to calculate this matching
Yeah.
integral. What's the point of doing the EFT in the first place? Because you're going to have to calculate your full integrals, right?
Right. So we'll come back to that.
Okay.
Yeah. So the difference, so I match is I over 16 pi squared g squared. And now you get log of mu bar over m bar squared plus 1 plus little m squared over big M squared times the same thing, and so on. OK. So the important thing about this difference is this is completely analytic in little m. The only m dependents are these power law coefficients. So as I said, the EFT is supposed to reproduce the infrared physics of the original theory. And it has done that because the difference, the error I'm making, I said was UV and local. And that's exactly what this thing is. There are no IR divergences. All the log m squareds and everything match. Yeah?
If we work in all orders of whatever and we want to do this matching, we would keep only terms up to the same order for both.
Yeah, that's right. So you have to decide what order you want to work in before you start the calculation. Yeah. OK. I'm taking the result here with the 1 over epsilon dropped, and this with the 1 over epsilons dropped, and subtracting. And that's what you get. OK? The other thing is this has no large logs in it. If I match at a mu bar of order the scale of the particle I'm integrating out. So perturbation theory is well defined. OK. Now, OK, maybe I should answer your question at this point. So what did we do here? We said that we had IF plus counter term and I matching minus IEFT plus counter term. And we saw that this was non-analytic in M. and this is also non-analytic in M. But the matching is analytic in M because it's a UV. It's the fact that the EFT and the full theory have some difference in the UV, which is short distance as far as little m is concerned. And so you get these local operators, I mean, just 1 and d squared and d fourth and so on. So now I can do a trick. I know that this is analytic in M. So I can just expand the right-hand side, both of these in M. And in dim reg, if you do this, all the non-analytic terms go away because you have things like m squared to the epsilons where the logs come from. But if you first Taylor series expand, you get 0. So let me expand this. I have IF expanded plus the counter terms minus I EFT expanded. And that's still IM. Expanded, and expanded here means little m. OK. So now let's see what happens. So what does, yeah?
So with every expansion that we do here, we're introducing new uncertainties, right?
No, there's no uncertainties.
Okay.
Because you're keeping all the terms. You have some order you're working to. You're keeping all terms up to that order. So
this new expansion doesn't introduce a new theory uncertainty?
no, because I'm just keeping, you'll see. Yeah, no, there's no uncertainties because you're keeping all the terms. You have your power counting parameter, and you're keeping all terms up to whatever order you want to work in. You're not dropping anything except high order terms. So if I'm working to 1 over m squared or whatever the leading order, I would keep this and drop all of that. That's not an uncertainty. I'm saying like in the weak interactions, I'm dropping G Fermi squared. I'm keeping everything to order G Fermi. So that's what I mean by controlled expansion. If I want to keep the G Fermi squared, I can do it. I have to just work harder and keep the term, and I can do the next order in the calculation. And it's been done in the weak interactions. I doubt if G Fermi cubed has been done, but you never know. OK. So let's first do the EFT expansion. So what have we done? Here's my EFT integral. And I'm saying I can expand this in little m as well. That's what the EFT expanded in little m means.
Sorry, what's in the parentheses in the superscript?
Sorry, what? Expand. I just mean expand. Okay. So expand here means expand in the infrared scale.
Got it.
So what is happening here is I'm taking this and I'm writing it. So now m is an infrared scale, so I'm expanding as though k is bigger than m, as 1 over k squared plus m squared over k fourth, et cetera. So now I have to do this expansion integral, which there's a whole series of terms here and a whole series of terms there. I multiply together to whatever order I want and then do the integrals. And what is this integral equal to? It's 0. In dim reg, there is no scale. All the propagators are pure k squareds. And if you go look at the dim reg formula, if you set the little m squared to 0, this integral is just 0. OK. Every term is 0. Because all the terms are some integral d to the dk times some k squared to some power. Positive or negative. All these integrals in dim reg are 0. It's still 0.
N equals 0.
Yeah. Integral d, this is 0 in dim reg.
Isn't there one special case of 1 power of n that is non-zero?
No.
Okay.
So thinking about the physics of what's going on here, if you set m equals 0 in that loop diagram, shouldn't you still get some value, like some contribution from the loop?
No, because what you're doing is you're dropping all the non-analytic stuff. And yeah, it's just 0.
Is there a physics explanation for why that would make sense?
Well, as I said, think of this integral as integration by residues. And there's no pole anymore in the integral. Right, you've gotten rid of the pole. I mean, this is not math, okay? So if you were doing a math problem, right, this whole series, there's some statement about the contour at infinity, it doesn't have to contribute and stuff, and that would all fail here, but we don't care. So it's 0. Okay, now let's look at what the full theory integral is. Expand it out. So I'm expanding out the infrared scale only. So the full theory integral will give me the integral of 1 over k squared minus m squared times 1 over k squared plus m squared over k fourth, and so on. Okay, because again, I'm expanding out little m. That's what I'm doing. So now you can integrate term by term. This is not 0 because I do have a pole at capital M. And you can verify, if you do this, that you get exactly that matching contribution. Where? Yeah. Because we're doing, there's, okay, what we're really doing is saying that we are doing some integral which is not the original integral that you're dealing with. And the difference between the two is some UV thing, and we're just comparing the IR part agrees, because by construction we made sure that the IR part agreed because we made sure we had this IR operator, wherever it is, this one, to match the IR. So the error you're making is in the UV, and we're doing the UV calculation by subtracting. And now I'm just giving you a trick to do the UV, show that this calculation can be done in a simpler way. Okay? Yeah?
What about the contour?
So this is finite, and that's finite, and you subtract to get something finite. So what you do is you do that, and you drop the 1 over epsilons, because you're only looking at the finite part. Yeah. Yeah.
Should I interpret this like an integral that is supposed to be 0 are just all the contour or all the 1 over epsilon?
Those are all the non-analytic pieces in little m, which we dropped. So I mean, where do logs of m squared over mu squared come from? They come from 1 over epsilons times m squared to the epsilon, and dim reg is starting expanding out. If you do a Taylor series expansion about m equals 0, these are all 0. Okay, the standard thing in dim reg is epsilon is either positive or negative or both at the same time to make sure all of these things are 0 as m goes to 0. That's what the dim reg formula is. You're analytically continuing from a region where this limit is 0 to the physical epsilon. So you're dropping all of these. But what I'm trying to say is that what I'm calculating, because it doesn't have, I know it doesn't have the logs in it, I can do the expansion. So we wasted some time, but okay, so how do you calculate the matching? I take the full theory diagram and expand in little m. That's what I do, and take the finite part. Okay, so that's in practice, that's what you do. So now this is way easier than anything, because you don't have to do the full theory diagram with 2 scales in it and 2 denominators or anything. You have expanded it out. You're only doing single scale integrals, because all the infrared scales have been integrated out. And if you have 3 propagators or something, multiple scale integrals are a complete disaster. You get dialogues and all sorts of stuff, but I've integrated it all out. So I have a single scale integral, and that's my matching. Yeah.
So how do you know that there aren't potentially important contributions to the IR theory in the infinite parts of that expansion?
Because the infinite parts are a short distance. I mean, the UV divergences and they're local. Okay. Otherwise, the whole renormalization, field theory wouldn't make sense. The whole renormalization procedure would fail.
All right, so you're coming, so now you're over here. So you're doing the full theory, you're doing this expansion in little m.
Yeah.
And then this,
So in practice, what you do is you say, here's the full theory diagram. I expand it out, and I do this integral. And I forget about all those two boards, right? I just do this integral. And it's a bunch of single scale integrals. And typically, the fact that you have a little m squared up top is going to tell you you're going to get a 1 over a big M squared in the denominator just by dimensional analysis, because you have more k's down here. So if I were working, for example, to dimension 6 or something, I would just do this integral and stop. Okay, so I'm trying to justify it, but in practice, that's what you do. And in some sense, you're picking out the contribution at big M, which you're missing in the EFT, and this works. I mean, this is how you do it.
so this integral that I'm doing, this IM or?
Yeah, it's IM.
Okay, all right.
So it's not that, it's, yeah. So the piece I put in the square brackets is this term. The next term with the k squared will give you that, and so on.
I see. Okay, so now I have, okay, so now I have IM.
One second.
And now I can do the full matching that I'm trying to do.
That's what you need.
Right.
Okay? So this tells me that those it's a different operator here. This is this XX operator that I have coming from the full theory loop. And I have all my coefficients, okay? It's this one for the first one, then there's a thing with the d squared, I have that, etc. Or whatever. So as I said, this is sufficiently simple that I have the whole infinite series, which makes it look simple, but okay, in the weak interactions, you don't, it's a more complicated structure. One second, the questions at the back, yeah.
If you have both of the low scale particles here, would you expand all of them?
Yeah, you expand out all the low scales. So the only integral has in it is the high scale. And now if you have multiple high scales, you've got to keep them all. So if you had the weak interactions and there was a W and a Z, you would have to keep the MW and the MZ. But the MB, M charm, M mu, whatever, they're all expanded out. Okay? And if you've done multi-scale integrals, there's orders of magnitude simplification. Yeah.
So is the way to think about this full procedure that we use the EFT Lagrangian to calculate everything in dimension 4, and then once you get to higher dimensions, you then go over to your full theory?
No, you never have to go over to the full theory. The EFT has everything in it, right? It's the O1 has the dimensions. This has I don't know what the dimensions are because I didn't say what X was, but let's say this is dimension 4, and that's dimension 6, and that's dimension 8, and you just have, everything's in there. You never have to go back to the full theory.
Okay. I guess then I'm confused about what's going on here, because this is not the full theory?
Yeah, but I have to do the matching to the EFT, right?
Sure.
So I take this thing and expand it out, and now the point is that you're matching. You have to know what the full theory is to do the matching. Otherwise, your EFT just has unknown coefficients, and you don't know what they are, and that's fine. You can work with that. But here, we have a perturbative. I'm doing an example of a perturbative matching where you can actually calculate the matching between the full theory and the EFT, and we're trying to do the calculation. And what I'm saying is that you can do this calculation by just taking the full theory integral and expanding out all the infrared scales first. It's a different answer than first doing the integral and then expanding. It's not the same. So you first expand and then do the integral.
You have to do some finite number of calculations in the full theory to do the matching.
Yeah.
So once you've done that, you can do as much in the
EFT as you want. Yeah. Now you can go calculate 100 processes in the EFT, and you don't have to go back and look at the full theory. You have my EFT Lagrangian, I just go, I do whatever. The weak interactions, I can go to B to CE nu. I can do CE nu plus a photon or whatever. I don't have to go back and do a new calculation of a matching for this process. The Lagrangian's a Lagrangian. I can just go calculate with it. One second, let's have some other question. Yeah. Go ahead.
So, oh, sorry.
Sorry, if I wanted for some reason to get these coefficients to higher precision in the two, is the procedure the same?
Same. Yeah, it's exactly the same. So you take the two-loop integral, expand out all the infrared scales, and do this. So these are single-scale integrals, and now, there's a huge technology of this with master integrals and Mathematica code, which automates it and everything. But that's where it's coming from. And basically, all high precision calculations are done this way, because we can't do them any other way. I can't do them any, but even the people who do them can't do them any other way. Okay, other questions? Yeah.
So do you match only for one particular diagram, or do you match for it?
No, all the yeah, you have to do the. So anything which is in the full theory which is not in the EFT. So you can see that this diagram is not in the EFT. Anything basically with internal heavy particles have to be matched.
And then this is matching. It will translate some term in the.
It's this term, yeah. We did it. I mean, these are the terms.
That's also the matching term.
Well, so the matching term is it's whatever is on the outside of this, right? So here we have an x and an x. So we're matching to the x squared operator. Whatever the external legs are, that's the operator. So I mean, I'm just treating the diagram and the operator as basically the same thing, because if you have whatever, I've drawn this as 4 photons because I said x was f mu nu squared, so this would be f mu nu squared squared. That's what the operator would be. Okay, because the external legs, which are, I mean, where did the diagram come from? It came from an operator in the Lagrangian. And so whatever the external operator is, I can just keep it that way. I don't have to draw any lines or anything. I'm only taking the internal fields and drawing the propagator. Yeah.
So the equivalent of the chi-squared operator and its coefficient
Is that? That's exactly right. Yeah, are we out of time? Yeah, so where are my notes? I think this is, well, let me make one other point, which is if you now go calculate in the EFT, the big scale M is not there in the EFT at all anymore. So if you start doing diagrams in the EFT, you can get logs of mu bar squared over m squared. You can never get logs of mu bar over capital M, because capital M is not a scale in the EFT. I mean, it's a number in front of the coefficient, but that doesn't mean you can't get logs. So in the EFT, if I set mu bar equals little m, there are no large logs. So I have little m, I have big M. I match here. I calculate in the EFT here. There are no large logs here. There are no large logs there. The problem is they're not the same point. But I can go from one mu bar to another mu bar by doing the renormalization group evolution. So you should have, OK, I'm not going to explain that if you haven't seen it. So and this is done in the EFT. So the anomalous dimensions in the EFT sum the logs of big M over capital M, which you can see over there, and do the full action. And in some sense, what you have done, so let me say this one last thing and stop, is what you have done is you've taken a log of little m over big M and written it as a log of m over mu bar plus a log of mu bar over m. So this is a 2-scale object, and you have split it into 2 single-scale objects. And this is coming from the matching, and that's coming from the EFT. So you've kind of put them in a different place. But it's orders of magnitude easier to do 2 single-scale calculations than 1 2-scale calculation. And so this is why this process is useful. OK, so I can take questions, but let's stop. Yeah, it seems like cheating, but it isn't.
I think the thing I was asking about earlier was the case of n equals -2.
Yeah, so there's OK, we can come back to that.
Okay.
Yeah, that's log, there's an IR to U, yeah, but it's still 0. But
Is the epsilon UV equal to epsilon?
it has to be, because there's only one epsilon.
Okay.
But yeah. Any other questions?
Questions here. if you have some time.
Yeah, sure.
Okay. So I think where I'm at, I understand every piece, but I'm trying to figure out how to put them all together. So, okay, we calculate this I matching term, this IM. Right away, we can do it straight from here.
Yeah, that's correct.
Doing this expansion.
Yeah, so you can forget about all this other stuff.
Okay. And so now I have this I matching, so I can do this IEFT where I expand.
Yeah, but EFT is 0 when expanded, see? So you don't have to even calculate it.
Okay, so then what am I? So this IM.
That's it. That's IM. And you're done.
Okay, so then where do I take this IM now?
So that's just the coefficients of these XX operators. So that gives you the EFT Lagrangian with the XX's. It's just whatever you get here.
Okay, so now I have this I matching. So the diagram I'm really talking about is with this guy integrated out.
So yeah, so you get this in the EFT.
Okay.
And now you do this, now you could do photon scattering or whatever you want to calculate in the EFT with this object.
Okay, so I go through, I calculate this. So this is, okay, this is my coefficient right here. This is, okay.
Yeah, so this is my L is this with some coefficient.
Okay. And we kind of took care of all the running with this mu and everything, and that's kind of all built into this.
Well, so I didn't explain the anomalous dimension, but because, well, if people aren't familiar with how you calculate it, but, so this would give me the matching at mu bar equals big M. And then I'd use the anomalous dimension in the EFT to take from C from, so we know C at big M,
Yeah.
and I run to C at little m.
Okay, so I guess this is kind of the last step that we didn't have time to get to.
Yeah, that's right. That's correct.
Okay.
From the anomalous dimension.
Okay, and then so sorry. Okay, so this part is clear. This next, and now how did these guys fit back into the story? These were.
They're there. They're still there. So we have, we have this operator, we have this operator, and now we're doing the one loop matching, which is this operator. And the problem with the toy example is that, yeah, this is also there. So there's a contribution to the 4x's from here. Okay, so the thing with the toy example is you're getting different sets of operators, but in the weak interactions you would take this diagram, expand out in the infrared scales, which is so you would have all of these are massless propagators in one W propagator, and that would give you the order alpha as correction to that 4 fermion operator.
I guess my question is more. I mean, this diagram, the procedure is clear. Now, here we also have this easier procedure, and I'm not sure how to combine these.
You just add them all up.
Okay.
So each one has a contribution to the Lagrangian.
Right,
so
we
this
have
one
this.
does not contribute because it's there in the EFT because, so we had this in the EFT from tree level. So this is there.
Yes.
This one is taken care of because of a loop from this.
Okay.
So just erase it. We don't need to worry about it. It's already in the EFT.
Okay.
Doesn't contribute to the matching.
This is just a correction if I want to do this.
No, it's not a correction. The full theory has this diagram.